let us continue from where we stopped. We talked about the metals, the trends are down the group. Now we are talking about halogens. These are the non-metals. Halogens are elements in group 7. They have 7 electrons in the outermost energy level, and that's why they are called group 7, as you can see. They have 7 electrons in the outermost energy level. Fluorine, bromine, and then we go to iodine. So they are all non-metals. So we want to look at the atomic radius and the ionic radius down the group. What happens? Atomic radius and ionic radius. The ionic radius and the atomic radius of halogens increase down the group. That is very correct. The reason is that as you move down the group, there is an increase in the number of energy levels. So if there is an increase in the number of energy levels, then it means that the ionic radius and the atomic radius will increase, obviously. Therefore, as you can see, fluorine with electron configuration of 2 to 7 has 2 energy levels. Chlorine with electron configuration 2, 8, 7 has 3 levels. So as you can see, 3 energy levels. So as you can see, down the group, the number of energy levels are increasing. Therefore, the ionic radius and the atomic radius increases down the group. So this is fluorine, chlorine, bromine, iodine, and then astatine. So atomic radius increases down the group, ionic radius increases down the group. We will talk about ionization energy later, and electronegativity, which is decreasing down the group. So we want to look at the fluorine, chlorine, bromine. So you can see the size. This is fluorine. As the number of energy levels increases down the group, the atomic radius increases, the ionic radius increases. That is very right. Now, atomic and ionic radius of the same element. Now, we want to consider, suppose we are considering chlorine, for example. What is the size of the ionic radius and the atomic radius? After gaining an electron, what happens? For the same halogen, the ionic radius, mark that, is larger or bigger than the atomic radius. For the same halogen, if you're talking about fluorine or chlorine or iodine, the ionic radius is bigger than the atomic radius. This is unlike on metals. In metals it is different, and here it is the opposite. So why is that the case? Halogens form ions by gaining 1 electron into the outermost energy level. That is very nice, very correct. Look at this. Chlorine has electron configuration of 2 to 1, 2 to 7. So how many electrons does it need to be stable? It needs 1 electron. Therefore, fluorine will react by gaining 1 electron, and it gains a stability of 2 to 8. Chlorine has electron configuration of 2, 8, 7. Therefore, it needs 1 electron to be stable. It requires a lot of energy to lose 7 electrons to have a stability of 2 to 8. Therefore, it is easier, it requires less amount of energy to gain 1 electron to have the stability of 2, 8, 8. Therefore, halogens form ions by gaining 1 electron into the outermost energy level. What does that do? The number of protons present in the nucleus remains the same. Very nice, very correct indeed. So the protons will remain the same, while the electrons will increase by 1. Yes, the electrons are increasing by 1, while the protons will remain the same. What will that do to the effective nuclear charge? The effective nuclear charge decreases. Remember, the effective nuclear charge is the force of attraction that pulls electrons in their outermost energy level towards the nucleus. But now this force has decreased. What effect will it have on the outermost energy level? Since the force has decreased, let us see. Therefore, valence electrons are less tightly held by the the effective nuclear charge decreases. Therefore, valence electrons are less tightly held by the nucleus, and thus the size of the ion increases. That's what I want you to understand. That as the number of protons remains the same, remember protons is directly proportional to the effective nuclear charge. If the number of protons, the atomic number is 17, then the nuclear charge, effective nuclear charge is 17. But now, 17 protons are supposed to pull 18 electrons towards the center. It is going to be difficult, right? Therefore, the effective nuclear charge decreases and the size of the ion of the halogen increases. That's why the ionic radius is bigger than the atomic radius. Thus, we'll start here. As the number of electrons is increased, the nuclear force of attraction is decreased. Thus, the ionic radius of halogens is bigger than that of their respective atoms. Very nice. So let me give you an example. Let us look at this example here. Let's look at this example. Chlorine. We want to look at this example. It is misbehaving. Example. Chlorine has the atomic number 17. We are okay with that. Which contain 17 protons. Very correct. So if it has 17 protons, it means the nuclear charge is 17. And the electrons are 17 before gaining an electron. But has 18 electrons and 17 protons on forming the ion. So after forming the ion, it gains 1 electron and the electrons becomes 18. The protons remain 17. Therefore, 17 protons present in the nucleus cannot pull 18 electrons towards itself. So if it cannot pull the 18 electrons towards itself, it means that the ionic radius is not going to decrease because it is not able to pull the outermost energy level electrons towards itself, to the center, to the nucleus. Therefore, effective nuclear charge decreases, and therefore the valence electrons are less tightly held by the nucleus, and thus the size of the chloride ion increases. Thank you. This is the chloride atom before gaining an electron, so it has electron configuration of 2, 8, 7 atomic radius. You can see it. How does it become stable? By gaining 1 electron. So now it has gained 1 electron and it has formed a negative charged ion here. So chloride ion is chloride ion, a negatively charged, which has an electron configuration of 2, 8, 8. So what has happened? It has added 1 electron here after gaining 1 electron. So this is the electron which has been gained. So you can see now it has 18 electrons. 1, 2, if you count all of them, they are 18. And the number of protons here at the nucleus, because protons are in the nucleus, they remain the same. So it is difficult for 17 protons, that is the nuclear charge, to pull these 18 like this towards this direction. It is not going to be easy. Therefore, the ionic radius increases. The ionic radius increases and it becomes bigger than the atomic radius. Electrical conductivity. All halogens are non-conductors of heat and electricity. Therefore, they are bad or they are poor conductors of electricity. They don't conduct electricity. The reason is that halogens are molecular compounds, and thus they don't have delocalized electrons nor free mobile ions for electroconductivity. Remember, delocalized electrons and mobile ions are responsible for conducting electricity in solid state and in aqueous state respectively. Therefore, halogens are molecular and thus have neither delocalized electrons nor free mobile ions for electrical conductivity. They don't conduct electricity. in melting and boiling point of halogens. The melting and boiling points of halogens increase down the group. The melting point and the boiling points of halogens increase down the group. The reason is that, remember, halogens, they are diatomic molecules. Chlorine exists as Cl2. Fluorine is F2. Therefore, they are diatomic molecules. So they have molecular structures. We know that. So if they are molecular structures, remember, chlorine is a gas. So if it is a gas, it is a molecule. So they are molecular structures. The molecules are held together by intermolecular forces. The intermolecular force is the one we call the van der Waals forces, which have to be broken during melting and boiling. So what happens down the group as the atomic size increases? As the atomic size increases, as the number of energy levels increases down the group, the strength of the van der Waals forces increases. The strength of the van der Waals forces, the one we call the intermolecular forces, increases as the size of the atom increases down the group. Hence, the melting point and the boiling point increases down the group. I want to look at now electron affinity. Electron affinity is the energy released when an atom in a gaseous state gains an electron to form a negative ion. And this one happens in halogens and the other metals. Therefore, electron affinity is the energy released when an atom in a gaseous state gains an electron to form a negative ion. What is the trend down the group of halogens? Generally, the electron affinity of halogens decreases down the group. Generally, the electron affinity of halogens decreases down the group. The reason is that as the number of energy levels increases down the group, the size of the atom increases. The force of attraction of the electrons in the outermost energy levels towards the nucleus decreases. So the nuclear charge decreases. If the nuclear charge decreases, then the EC with which electrons are gained decreases. So the EC with which electrons are gained decreases. So down the group, the EC-ness of gaining an electron decreases as you move down the group. As the atomic radius increases, the EC of gaining electrons decreases. Therefore, fluorine will gain an electron very fast compared to iodine. Iodine will require a lot of energy to gain one electron because the atomic size is increasing down the group. Reactivity of halogens. We want to see which one is the most reactive and then which one is the least reactive, and then we look at the trend down the group. The reactivity of halogens with metals decrease down the group. So the reactivity of halogens decreases down the group. So in this group, fluorine is up there, is the most reactive, followed by chlorine, bromine, then iodine is the least reactive in this group. The ability of an atom to gain an electron in its outermost energy level decreases as the size of the atom increases. We have talked about that. As the size of the atom increases, the nuclear charge decreases, and then it becomes very difficult for an electron to gain an atom as the size increases. Hence, the decrease in the activity of halogens down the group. We can put it in other words. In other words, we can say that the reactivity of halogens decrease down the group because the reactivity of halogens decreases down the group because halogens react by gaining electrons. The ease of gaining an electron decreases down the group as the atomic size increases. The easiness of gaining electron decreases down the group as the atomic size increases. This leads to progressive decrease in the force of attraction of electrons in the outermost energy levels by the positively charged nucleus. So down the group, as the energy levels increase, the nuclear charge becomes very little, decreases, and the ability for the atom to gain an electron as the size increases down the group becomes difficult. Therefore, this element is very unreactive when you compare with this one. Fluorine is the most reactive because the ability of gaining one electron in fluorine is very high, and the ability of chlorine gaining one electron is higher than that of bromine. So the most reactive, followed by chlorine, bromine, and then iodine. As the atomic radius increases down the group, the nuclear charge decreases, the ability to gain an electron in the outermost energy level decreases. Properties and trends across a period 3. Now we want to look at period 3. What are the trends across the period? But before that, we want to look at this. Across the period, we have metals and nonmetals. So we start with sodium, atomic number 11, magnesium, atomic number 12, aluminium, atomic number 13, silicon number 14, phosphorus number 15, sulfur number 16, chlorine number 17, and then finally argon number 18. So let us look at the trend across the period. The electron configuration, as you can see, the outermost energy level here, the number of electrons in the outermost energy level increases by 1 as you move across the period. 1, 2, 3, 4 to 8. You can see that. So atomic radius is increasing. And remember, nuclear charge, it is important to understand that we defined what is nuclear charge in the beginning. So nuclear charge depends on the atomic number. If the atomic number is for 11, the atomic number is 12, therefore the magnesium has got higher nuclear charge than sodium. Nuclear charge depends on the atomic number. So 18 has very high nuclear charge, force of attraction, compared to sodium. So nuclear charge increases as you move across the period. Nuclear charge increases as you go across the period table, the periodic table, due to an increase in the number of protons. The protons are increasing because there is an increase in atomic number as you move across the period. Then I want to remind you what is a nuclear charge. The nuclear charge is the total charge of all of the protons in the nucleus. Therefore, you should know that the nuclear charge has the same value as the atomic number. If the atomic number of an element is 18, the nuclear charge is 18. If the atomic number is 11, the nuclear charge, the force of attraction, the force that is pulling the outermost energy level towards the nucleus is 11. Here the force of attraction pulling these 8 electrons towards the center, towards the nucleus is 18. So you can see, you cannot compare the force of 11 and the force of 18 because the nuclear charge depends on the atomic number. It is important for you to understand this because as we are going to explain across the period, you need to understand the nuclear charge. It is the base. Across the period, the atomic and ionic radius. The atomic radius of period 3 elements decrease across the period. The atomic radius decrease down, across the period. Why is that the case? For the same number of energy levels, the number of protons in the nucleus increases by 1 across the period. This leads to the increase in the nuclear charge, while the shielding effect remains the same, hence decrease in the atomic radius across the period. Let us put in another way. This is because the number of electrons of an element increases as you move across a period, which means that the number of protons also increases. The nuclear charge increases as the number of protons increases. This increases the strength of the force of attraction between the nucleus and the electrons in the energy level. So the electrons are pulled inwards towards the nucleus. This contracts the radius inwards, and therefore the atomic radius decreases. So let me use this to explain this. So across the period, the nuclear charge increases, therefore the outermost energy level electrons are pulled strongly in argon compared to sodium. Therefore, the nuclear charge increases across the period as the atomic radius decrease across the period. So graphically, we can represent atomic radius, the y-axis, and then the ionic. So graphically, we can represent the atomic radius across the period like this. So this is atomic radius, and this is the atomic numbers across the period. So atomic radius decreases as you can see the graph going. So from sodium, magnesium decreasing down. So atomic decreases across the period. Electroconductivity. Sodium, magnesium, and aluminum are good conductors of electricity. The reason is that they have giant metallic structures which contain delocalized electrons, which are responsible for conducting electricity. Electrical conductivity increases from sodium to aluminum. That is correct. Electrical conductivity increases with an increase in the number of delocalized electrons. As the number of delocalized electrons increases, the electrical conductivity increases. Aluminum is a better conductor than magnesium, and magnesium is a better conductor than sodium. Phosphorus, sulfur, chlorine, and argon do not conduct electricity. They have molecular structures, and all of the electrons in the atoms are used in bonding. Thus, they lack delocalized electrons or free ions for electrical conductivity. Silicon conducts electricity or electric current, and it is electrical conductivity increase with increase in temperature. As temperature increases, electrical conductivity of silicon increases. The reason is that the silicon is a semiconductor, making it very unique. Graphically, electrical conductivity increases from sodium, magnesium, and then aluminum has the highest conductivity, and then it decreases to silicon, and then the rest they don't conduct electricity, so it decreases. So this is the graph that represents conductivity of elements across period 3. Melting point and boiling point. Sodium, magnesium, aluminum have very high melting point. The reason is they have giant metallic structures with strong metallic bonds, which need a lot of energy to break. Actually, you should know that boiling point and a melting point depends on the structure the structures of an element or an atom. Those structures with giant metallic structures, molecular structures, the melting point depends on the structure of an element. The trend, the boiling point and melting point increase from sodium to aluminium. As you move across the period from sodium to aluminium, the nuclear charge increases while the energy levels remain the same, hence decrease in atomic radius. The smaller the atomic radius, the stronger the metallic bond, and therefore the boiling point increases from sodium to magnesium. Silicon to an metal has very high melting point and boiling point. The reason is that silicon has giant atomic structure. Like I said, boiling point, melting point depends on the structure of an element. Silicon has got giant atomic structure which contains a strong covalent bonds that require a lot of heat to break. Therefore, it has a very high melting point. Phosphorus, sulfur, chlorine, and argon have low melting point. You know why? They have molecular structures. They are structures made of molecules. So they have molecular structures with strong covalent bonds between the atoms, except in argon, but weak van der Waals forces between the molecules, which are easy to break. So the molecules are held together by strong, the atoms of these molecular structures, the atoms are held by covalent bonds, but the molecule is held by weak van der Waals forces that requires very little energy to break. That's why molecules, they have very low boiling and melting points. Graphically, this one is represented the melting point. So the melting point increases from sodium to magnesium and then aluminium, and then it shoots very high to silicon, because silicon has got a very high melting point, 1800 degrees Celsius, and then it decreases to phosphorus, decreases as you move across the period. Reactivity, the reactivity among the metallic elements decrease across the period from sodium to aluminium. Reason there is a continuous increase in the nuclear charge from sodium to aluminium, which leads to increase in ionization energies, hence increasing difficulty in removing an electron from the outermost energy level. Among the non-metallic nanometals, reactivity increase across the period from phosphorus to chlorine. There is an increase in nuclear charge from phosphorus to chlorine, hence an increase in the EC of electron gain. Argon is unreactive and can only react under very special conditions.